All right, guys. Who's ready for some more trig? Who's ready for some more trig?
Oh, yeah.
Woohoo! All right. Let me give you a piece of advice on this trig. A lot of it's going to be some memorization. Every year I struggle with whether or not I should show you all the proofs because I always wanted to see a proof. I'm like, bull crap, that works. Like, I always want to see where it came from. So in your book, I've put all the proofs in there. I might do one of them, depending on the time we have today, or whatever. The proofs are kind of nasty, and what normally happens when I show everybody the proofs, people's brains start exploding. Now, some people don't. Some people are like, ooh, I love that. And again, they're all in your notes, so you can look at it. But I might show you one of them and just kind of maybe point out and help you where if you really care about that kind of stuff and you're interested in where these formulas come from, great. But I got to be honest with you, being able to prove them is probably not going to be the way you memorize it. Because now there might be some like that, and when they are like that, I'll show you. But these initial identities, we're going to be talking about trig identities. These are relationships in trigonometry that are always they're always true. And we're going to use those to start really delving into this trig. I'm going to give you an assignment sheet right now. And on this assignment sheet, you are going to see at least 4 quizzes on identities. All right? I have a 5th one, but I don't think I'm going to use it. But you're going to see right here, the first one is going to be tomorrow. And the identities we're going to talk about tomorrow, I think I've already talked about. But I'll talk about them again today and show you some of the proofs of those, should that possibly help you. But ultimately, you have got to start memorizing these. All right? And I'll talk about which ones are which, and you'll see when the quizzes are going to occur. And then, at the end of the day, I'm going to drop your lowest one. For your sake, please don't let the one that I drop be this first one. Because the first one is the easiest one. Right? So you want to rack up a 20 out of 20. But you can get an 80 out of 80 on these just by knowing your trig identities. Not applying them, just knowing them. And an 80 out of 80 can give your grade a boost. Okay? And a lot of people are going to need a boost because historically, average-wise, this is the hardest test I get. Sorry. Now, I hear every year somebody say they'll be doing problems and they're like, I love this stuff. It's either a love-hate relationship usually. But I can tell you this, that people that hate this stuff are the ones that don't know their identities. Because if you don't know the identities, it's like, I don't know, it's like playing middle linebacker at Alabama. If you are thinking and not reacting, you're not going to be a good player in Nick Saban's system. You're just not. You got to know it so well that when you are in a situation, you are reactionary. And the way to do these problems is to know your identities so well when you look, and it's not that hard, there's not that many. Okay, that when you look at a problem, you go, ooh, I see a blah in there. Oh, I see a so-and-so in there. Oh, that simplifies to this. When you get to that point, you're going to be in a lot better shape with this identities, and you'll probably like this chapter versus some of the others that just kind of go, oh, I memorized everything the day before the test, I'll be fine. No, you won't, not on this chapter. Well, maybe a couple of you, but not many of you. So if you keep up, you're not going to hate this, okay? So I am going right now back to the book, and it's book number 4, and I am trig identities, maybe. Nope. Okay, it's growing. Okay, so trig identity starts on page 35. So I am 35, and the first identities we're going to talk about are the Pythagorean identities. Now, we've already talked about these, but I'm going to talk about them again, and I'll put the proofs right here. Now, the bottom line is you need to know these 3 that are boxed in on the bottom in all of their infinite forms. Now, there's actually not an infinite number of forms, but what I mean by that is sometimes you're going to see the expression sine squared plus cosine squared, and you're going to have to know how to simplify that. Well, sine squared plus cosine squared is 1. But sometimes you're going to see the expression 1 minus cosine squared theta. Well, what's 1 minus cosine squared theta equal to? sine squared theta. Sometimes you're going to see the expression cosine squared theta minus 1. What would cosine squared theta minus 1 be? Negative sine squared theta. Did y'all see that? So it could show up a lot of different ways, but what I hope triggers in your brain, whenever you see any two of these three parts, if you see a cosine squared with a 1, or a sine squared with a 1, or a sine squared with a cosine squared, if you see any one of those two, then think back to the equation and then just solve it for this, and you'll know what the other part's equal to. And you've got to get better at thinking that way. Heck, even if you saw that and you're like, okay, I don't know what that is, but I do know this. And if I solve for cosine squared, I get negative sine squared theta. I'm going to replace my cosine with a 1 minus sine squared theta. Replace the cosine with a 1 minus sine squared theta, and what do you end up with? Negative sine squared theta. Are you with me? So you've got to know this one right here, this one right here, and this one right here. And you've got to know them backwards and forwards, inside and out, because you're going to see parts of them in different ways. Like you might see secant squared theta minus tangent squared theta. What is secant squared theta minus tangent squared theta? 1, right? Because I would subtract the tangent squared to get this, and I'd be left with a 1 over there. You might see 1 minus secant squared theta. What's 1 minus secant squared theta? Negative tangent squared theta. Do you see that? But because I would have to subtract the tangent squared theta to the right and subtract the secant squared to the left to get this. So that would give me negative tangent squared theta. These are all identities, but you can't memorize every single version. So you memorize these three, and then when you see something like a 1 with the secant squared together, hopefully you go, oh yeah, I got an identity that has a 1 and a secant squared. Let me solve that identity for this and see what's left over. If you ever see a cosecant squared and a cotangent squared together, you remember this identity. And by the way, I wrote this tangent squared plus 1 and 1 plus cotangent squared because that's what it looked like here. But most people write it as cotangent squared plus 1. I would say most people, a lot of people. So obviously you can change the order of the two pluses, right? All right. But anyway, know these three. These are called the Pythagorean identities. And they're called the Pythagorean identities. And again, I think I did these proofs earlier, because if I took a triangle that's right, and I wrote out the Pythagorean theorem, which I did, right? And here I divided everything by an r squared. Here I divided everything by an x squared. Here I divided everything by a y squared. And then I used my trig functions that stood for y over r. What is y over r? Y over r, if that's theta. The sine of theta is what? Y over r. So I replace that with sine of theta. And sine theta squared is, that's right there. What is x over r when you square it? X over r, based on that theta, would be cosine of the angle, right? Because the trig function is just a ratio, right? So I put a cosine in there and square it. And then r squared over r squared is 1. That's why this exists. And when I do that with all of these, what's y over x? Y over x with respect to theta? Tangent. X over x, 1. What's r over x? Well, if x over r is cosine, what's r over x? Secant. Secant. That's why that one's squared. And then you get over here, y over y squared is 1. What's x over y? If y over x is tangent, what's x over y? Cotangent. That's why that one's squared. And if y over r is sine, what's r over y? Cosecant. That's why that one's squared. So you don't have to regurgitate these rules. You don't have to prove this on your test. You just have to know how to simplify those. So on your test, you will probably see something like 1 minus cosecant squared theta equals blank. And you'll go, man, what identity had a cosecant squared and a 1 together? Oh, that was this one. Cotangent squared theta plus 1 was cosecant squared theta. So you remember that and you go, all right, how can I turn that into this? If I subtracted a cosecant squared, I would have that. So I'd have to subtract a cotangent squared. Oh, it must be negative cotangent squared. That's what a question on your test tomorrow might look like. Y'all with me? Okay, Those are the Pythagorean identities, and those constitute the first part of your fundamental ones. Your fundamental ones are the really basic ones that we don't have, that aren't really dirty, okay? So that's the first one. All right, here is, and by the way, again, they could get really ugly. Look, I could take this, where I guess I really didn't solve it. I could solve completely for sine. It might even look like that. If I squared, like if you got it down to this, isn't this a variation of sine squared plus cosine squared equals 1? And if I square root both sides, what do I get? Sine of theta, right, equals plus or minus that. That would be another version of this identity. You can really get a little dirty with all of these, but those are Pythagoreans. All right, here are the co-function identities. I think I've talked about these too. You might remember, isn't the sine of that one the same as the cosine of that one? It's complement. So if I said the sine of 20, that would be the same thing as the cosine of that one. 70, because 20 and 70 have to add to 90, right? On a right angle. If I say the tangent of 10, that would be equal to the cotangent of 80. So those are the co-function identities. This is a little proof of them. Look, the sine of the theta is y over r. The cosine of the beta is y over r. Well, if sine of theta and cosine of beta are both y over r, then the sine of theta is the cosine of beta. And beta is just 90 minus that. That's what gives you these co-function identities right here. And there's 6 of them, right? And they go together, sine, cosine, tangent, cotangent, secant, cosecant, whatever, all 6 of them work, but all it means is tan, co-tan, cosecant, whatever, cosecant, secant. They're all linked like this, one or the other, and all you got to do is say whatever this is, 90 minus the other. Whatever that is, 90 minus the other. And how do you normally see it? Something like this. Cosecant of 12 equals secant of blank. And you'd say, what's its complement? 90 minus 12, whatever adds to 90, right? Or I could be a little tricky, maybe. Tangent of negative 10 equals cotangent of blank. 90 minus that, right? Because they have to add to 90 if they're complements. Y'all tracking with me? Or it could be really sneaky. Sine of pi over 5 equals cosine of blank. Now, are you going to go 90 minus pi over 5? No. Why not? Because that's a radian. So what are you going to do? Pi over 2 minus pi over 5. And yeah, you're probably going to have to find a common denominator and clean that up a little bit, right? But that would technically be true. So anyway, those are the co-function identities. And the co-function identities are also part of this fundamental identity group. All right. Now you also have, moving past, even and odd identities. Now you might remember when we were dealing with functions that an even function has what kind of symmetry? Y-axis. Y-axis. Now think about a parabola. That has y-axis symmetry if I haven't shifted it, right? Y-axis symmetry. What do you know about x equals 2 and x equals 2 and x equals negative 2? Same y value. What about x equals 4, x equals negative 4? Same y value. So opposite x's give you same y's. That's what that means. Opposite x's, same positive y value or negative y value, whatever. Same y values. This means opposite x's, opposite y's, plus minus. That's an odd function. They don't have y-axis symmetry. They have what kind of, those are like this. Opposite x's, opposite y's. Opposite x's, opposite y's. Like a x cubed graph, right? Well, trig functions are either even or odd too before you shift them. But the only ones that are even, you will find out when we graph next, the even ones are cosine because the y-axis is right here and the cosine does this. All right? And all the cosine and its reciprocal, right? Because a secant, like a cosine, it's based off a cosine. So the only ones that are even are cosine and secant. That's it. Which means opposite x's are opposite angles, same y values. Bottom line, what can you do? Opposite angles, same sign on the y value. So what does that basically mean if you have a cosine or a secant of a negative? What can you do with a negative?
You can
throw it away. You can literally just throw it away. It's gone. So if you ever see like cosine of negative 50, same as cosine of positive 50. If you ever see secant of negative 18, same as secant of positive 18. You literally can throw the negative away. It kind of makes sense. Think about it. What's the cosine at 30 degrees? Over a lot? Root 3 over 2? What's the cosine at negative 30? Still over a lot. Square root of 3 over 2, right? Opposite angles, same value. Opposite angles, same value. So you can throw the negative away when it's even. Those are the only two evens. All the other ones are odd. Now, what does it look like I'm doing on the odds? What does it look like I'm doing?
Just move it to the outside.
I'm just moving it to the outside. So if you see sine of negative 50, you could rewrite it if you wanted to as a negative sine of positive 50. It's almost like factoring it out. Y'all with me on that? That's all the rest of them are odd. And you'll see that when we graph them. On a y-axis, cosine starts here and goes down, makes a nice mirror image. Sine goes up on one side, down on the other. It's kind of like a y cube graph, except it kind of looks like this, right? If this was the origin. It bumps up here, bumps down there, and you can see it has that origin symmetry, all right? But anyway, that's what odd functions do, but that's all you would have to know. You might see something like, hey, what's cosine of negative 30 simplified to? Or maybe I don't give you negative 30 because you could actually do the math on that. What if I said cosine of negative 10? Well, what can I do with that negative? Toss it. Cosine of positive 10. But what if I said, what's sine of negative 10? I could move it to the outside and say negative sine of positive 10. That's what the even or odd identities allow you to do. That's about it. Okay? And blah, 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 blah. So moving on. Do I not give you the identity sheet right here? Hold on. I thought I gave you one with all these on there. Probably do eventually. Hold on. There they are. So if you go to your page 43, the first quiz is going to be over all the fundamental identities. Now, obviously, this first column, those are just your trig identities, right? Just your trig identities. So if I said, what is y over r the same as? You would say, oh, that's your sine of your theta. If I said, what's x over y? You would say that's the cotangent of your theta. Okay? And then you know about reciprocals, right? Sine of an angle is the same as 1 over cosecant, right? Or 1 over sine is the same as a regular cosecant. You know they're reciprocals of each other. Those are also fundamental identities I might quiz you on. So more than likely, you'd see something here on the right, and I would say, what's 1 over cotangent? You would say tangent of theta. Okay? And then you know that tangent of an angle is the same as sine of the angle over cosine of the angle. And cotangent's the cosine over the sine. Why? Because isn't sine y over r and cosine's x over r? And what happens when you divide y over r by x over r? You multiply by reciprocal.
Y over x.
And you get y over x. And what's y over x?
Tangent.
Tangent. So you got to know when you see a fraction and you got a sine over a cosine of an angle, that's a tangent of an angle. When you see a cosine of an angle over a sine of an angle, that's a cotangent. Those are identities that we have to know. And those are called reciprocal identities. And I believe those are called quotient identities, although I don't ask you about those. The only ones you're going to probably have to know the name of are Pythagorean, because sometimes I'll just say, what are your 3 Pythagorean identities? And I want you to write out sine squared theta plus cosine squared theta equals 1, tangent squared theta plus 1 equals secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. And by the way, don't forget the thetas on these. People all the time they write tangent is sine over cosine. No, it's tangent of theta is sine of theta over cosine of theta, because you're always saying the ratio with respect to this angle. So don't forget the angle in there also. Y'all with me? And then your function, your Pythagorean, and your even or odds, those are the new ones we talked about today. So those 6 little groupings on that front page, that's your quiz tomorrow. 20-point quiz. It's the easiest of all the quizzes because most of these we've talked about already a decent amount. Okay? Then on your next Tuesday, We're going to do double angles, and that's going to be the priority. We haven't talked about those, nor will we today. We're going to work on double angles on that quiz and anything else. So the double angle identities will count a little bit more, maybe like 3 points apiece. And then I'll fill it in with some random, these fundamentals. And then Wednesday, we'll have talked about half angles, and we're going to quiz you on the half angle identities. Those are going to be prioritized in terms of value, maybe 3 points apiece, and the rest of them might be 1 point apiece or something like that. And then we're going to have the weather day on that Friday next week. And then we'll come back on the Monday, and I'll give you the last identity quiz over all of them. You with me?
So are they each cumulative, or is it just the last one?
Each one after this first one, notice it says and the priors.
Okay.
So but the highest point values will be on the new ones that are introduced on that quiz. So it might be like 3 points, 3 points, 3 points, and then I fill in the other 11. So these fundamental ones, definitely know them. But if I were you, I'd get flashcards, especially if you stink at memorizing stuff, and put all these on flashcards and just start going through them. And when you get to the point where you're so bored about them, you're like, of course I know that. And I'll limit those and just start going through the ones that are still giving you trouble. And if you do that now, by the time you hit your test on the 20th, you'll know these identities so well. If you start now, that you won't have issues with these. But some of these start getting a little nasty. I mean, look at these double angles. Right? Look at these these are actually, those are alpha plus beta identities, which we'll talk about. These are double angle identities. These are half angle identities. I don't know that we're getting into these this year, but you can see that these aren't super easy to memorize. You're going to have, and the proofs are not going to help you a lot. You're going to have to know these to do well on this test. And if you don't, it's going to be no fun for you. I'm telling you, there are always people that make their lowest test of the year on this. And there are always people that go, man, I like this stuff. It's kind of cool. But the people that like it are the ones that know their identities early and often. And here's the nice thing. Even if you do stink on this test, you can still offset it with an 80 out of 80 if you memorize your identities, right? So you could make a 50 out of 100 on a test, but get an 80 out of 80, and you got a 130 out of 180, which granted, even though that's not absolutely joyous and you're not going to scream home to mom about it, a 130 out of 180 at least brings your cumulative thing up to a 70%, 72, right? Which beats the crap out of a nasty 50, right? So you can still salvage yourself. And on top of that, remember, you can always drop your lowest test grade if you get an A or B on your exam. Go back and drop it. You still are sitting on your 80 out of 80. All right, and I will drop your lowest one. So if you do have one bad one, like maybe you're all I won't drop the very last one though. That's you showing me you know everything. But any one of the first 3 or 4 that we get to, if we do 5, any one of those first 4 or first 3, whatever, I will drop your lowest one if there's one in there to drop. I'll keep them if you do well on all of them. Okay, let's move on. Simplifying trig expressions. We're going to talk about that real quickly. And then if I have time, I will go back and if I have time, I will go back and look at some of these proofs. Okay, so real quickly, let's take a look at simplifying because you're going to see a little bit of that today. So check it out. What would you do using the identities that you have? So if you want to get your identity sheet out, you can, because I know you might be still a little rusty with these. How would you simplify this expression? Cosine theta, cosecant theta. Now, this thing right here, each of these has a value. And if I use my identities, I might be able to replace one with its identity and clean this up into a smaller value. Now, you're used to seeing the word simplify. And what do you normally do when you see simplify? You PEMDAS, right? And PEMDAS, actually, remember, there's no F actually in factor in PEMDAS, right? There's no F for factor, unless factoring helps you divide, in which case you'd want to do it. But simplifying here is not quite PEMDAS. Simplifying here is this. It's looking at ways to make this big expression smaller. And there's not that many clear-cut rules. So I've come up with some, and here they are. First thing is, if you have a denominator, sometimes it's helpful to take that denominator and express it in a way that it's now in the numerator. Like for instance, what would a sine of theta in the denominator be?
Sine.
A sine in the denominator is the same as a,
R over Y. So it's
okay, well, think it's a cosecant
cosecant.
in the numerator. Or what is a cotangent in the denominator?
Tangent.
A tangent in the numerator because of your reciprocal identity. Rarely are you going to get anywhere changing. Well, you might get there, but it's not going to be great. Changing things to y over r and x over r. Try to avoid doing that. Okay? If you're doing that initially, I understand, but try to avoid it. It usually makes a mess of things. All right? If that doesn't help you, try converting to sines and cosines. Isn't everything really convertible to sines and cosines? Think about it. What is a cosecant the same as?
1 over.
A cosecant of theta is 1 over a sine of theta. What's a tangent equal to?
1 over cotangent.
Well, in terms of sine and cosine, a tangent of theta is a sine of theta over a cosine of theta, right? That's converting it to sines and cosines. What's a cotangent of theta? A cosine of theta over sine of a theta. So I can convert anything to sines and cosines, and that makes it a lot easier to see what cancels. Because if I can convert everything to sines and cosines, I can see, oh yeah, that sine canceled with that sine, and that cosine canceled with that one. So sometimes that's helpful. Third thing, use your fundamental identities. You're going to see that on all of these that we do. I go to my fundamental identities, and I just write a reciprocal there, and something cancels. So think about that. Or maybe I use the Pythagorean identities to change the sine squared plus cosine squared into a 1. That certainly looks better, right? Fifth thing, factor the polynomial. I normally don't want to factor to simplify, but sometimes when I factor, it makes it easier to see that something else might cancel. All these things we're going to look at. Again, I'm doing it to simplify. So maybe I'm talking about division. And then add fractions. Sometimes I'm asking you to add an identity to another one. Well, how do you add fractions? Common denominator, and then maybe something. These are all suggestions. And then finally, create a monomial denominator. I'll have to show you an example for that. That's one of the really trickier ones. That's why I listed last. But the very last thing, don't just sit and stare at this. Every year I have somebody walk up to my desk and be like, man, this thing's impossible. I was like, man, that is tough, man. I said, what have you tried? I tried everything. I was like, okay, well, let's take a look at it. Have you maybe tried putting it all in the numerator? Oh, well, I can try it. And they tried, and like, look, nothing happened. I'm like, you're right. Have you maybe tried like changing it all to sines and cosines, see what would happen? And they're like, oh, right. Okay. And literally, all I'm doing is reading from this list to them. And eventually they get it, and they're like, man, it's always easier when you do it. And I'm like, literally, I'm giving you a guide. It doesn't necessarily work in this order, but again, if you get stuck, try something from this order. And literally, I created this list because I've done every identity problem I've ever seen, and every identity problem I've ever seen can be simplified with that list. So with that being said, let's take a look at some of these. Okay, so right here, what could I do to simplify that?
You can change it to X's and R's.
Remember I said try to avoid that with the plate. I could change it all to sines and cosines. Now this already is a cosine. How could I change that to a sine and cosine? 1 over sine theta, which happens to also be using a fundamental identity, right? So I'm actually doing both. I'm changing the sines and cosines and using a fundamental. So cosecant is, I'm going to leave it there actually. Cosecant is the same thing as 1 over a sine of theta. So that gives me what? Cosine theta over sine theta? Is that helpful? Oh my gosh, that's cotangent of theta. Does this look more simple than that? Yes. Now, I don't want to change that to 1 over tangent because 1 over tangent is less simple than that. All right? This is a single expression. And I don't want to change something that's in the denominator when it could be in the numerator. So I'm good. All right, look at this second one. What if I gave you cosine t, or I'll stick with theta. I think maybe these come through your book. That's why I'm numbering like this, but whatever. Cosine theta over cotangent theta. Any ideas?
Change it to sines.
Change it to sines and cosines? Now you can, but then you end up with a fraction within a fraction, don't you? What would be another thing you could do? What's the very first rule? Represent everything in the numerator? What is a cotangent in the denominator the same as? So a cotangent in the denominator is a tangent in the numerator, because this is technically 1 over cotangent, which is tangent. Now what could you do? Change it to sines and cosines. So a tangent is sine of theta over a cosine of theta. Oh my gosh, what happens? And you're left with sine of theta, which, I gotta be honest with you, looks a lot better than that. All right, what about this?
What?
What about secant phi minus 1? What is phi? Just another angle. Who cares? It's not the null set. It's the Greek letter phi. It's a lowercase phi. It probably looks, well, it does look like that. Here's uppercase phi and lowercase just kind of looks like that. Just another angle. They're trying to expose you to different variables. Now, I don't have any rule. Now, I do remember secant squareds being with 1, right? Remember those Pythagorean identities? Tangent squared plus 1 is secant squared. A secant squared and a 1 are in that identity, but it's squared. These aren't squared, so I can't use that right this second. Anybody got any ideas? Did you multiply it out?
Yeah.
Okay, so what is that times that? Secant squared of phi. What does outside and inside do? And you're left with secant squared minus 1. Now, I do recognize an identity that had a secant squared and a 1 in it. I got to know it, though. It is tan squared theta plus 1 is secant squared theta. So based on that, what would that be equal to? Y'all see that it would be equal to tan squared of phi? Because right here, if I subtract 1, there's my secant squared theta minus 1. That's this. So it must be equal to the tan squared theta, or in this case, tan squared of phi. And I think it's phi if you go anywhere else in the world, but we say phi in America. I don't know why. All right, what about, but you're going to start seeing these. By the way, these get really dirty, but not tonight. What about this one? What about cotangent of t, secant of t, sine of t? Any thoughts? Changing the sines and cosines. Okay, what's cotangent of t?
Cosine over sine.
Cosine of t over a sine of t. What is secant of t? 1 over a cosine of a t. And then sine of t is already a sine or cosine, right? What happens? Oh, look at that. Everything cancels but 1. Who knew that was equal to 1? Like if you really loved your sports team, you could go, we are number cotangent t secant t sine t. And only the really good nerds would know you're going, we are number 1. Exactly. All right, what about this? I just put that on video. That's terrible. All right, what about cosecant x sine x minus cotangent x tan x? Okay, we could try moving it to the numerator. What would that mean? Or we could move to the numerator. That would become a what? A cotangent? So that would give me what on top? Cotangent squared. Do y'all see this? And by the way, guys, there's not one way to do this. There's a ton of ways. Well, I'll show you a couple ways on this one. All right, so that's that. And then what about this? If I bring a sine up, it becomes a what? Another cosecant. So you'd have a cosecant squared. Oh, wait, I've got an identity that has a cotangent squared and a cosecant squared in it. Now, you don't think that if you don't know your identities. If you don't know your identities, you go, duh, I don't know what to do. But if you know your identities because you've memorized them, you go, wait a minute, I remember that cotangent squared theta plus 1 was cosecant squared theta. Is that this? Yeah, if I subtract the cotangent, I end up with that equals 1. So what is this? 1. Now that's one way to do it. Here's another way to do it. Change all the sines and cosines. What would that give me? Sine on the bottom. What is cotangent? cosine x over sine x. What is tangent? Sine x over cosine x. How do I divide a number by a fraction? I multiply by the reciprocal, which is cosine x over sine x. So this time I have 1 over sine squared minus what? Cosine squared over sine squared. What's one of the rules you have? What are one of the rules you have? Look down there. It's the 6th one, I think, maybe 7th. Add fractions. How do I add these two fractions?
Like,
You got a common denominator, right? So I get this. Oh, wait, 1 minus cosine squared. I have an identity that has a cosine squared and a 1 in it. It's this. Sine squared theta plus cosine squared theta equals 1. Well, if that's true, what is 1 minus cosine squared theta? Sine squared? So I can replace the top with the sine squared. And what do I end up with? Still 1. Now, much more difficult path to get there, right? But your path's not going to be my path, necessarily. I mean, what I do is what pops into my head initially. But that may not be the best way. There many a time have I done an identity and somebody goes, you could just do this. And I'm like, yeah, that would be a lot better. And the same thing's going to be true for you. You might take a long, long path to get there. And then I might go, you could have just taken a reciprocal or blah, blah, blah. So don't worry about that. As long as you get there, you get there. Right? Right? I mean, unless you're like in a race or something. Obviously, if you're doing a 100-meter dash and you head the wrong way, yeah, you go around the world, you can eventually get to the finish line, but it's probably going to take a while.
why is it that you don't use like the X's and the Y's more? Because I feel like it's so much more.
Because these are baby identities. They really are. I mean, you're going to see identities that are like 15 expressions in there, and if you start putting Y's and X's, you're just going to get lost in it.
Okay.
Just trust me. Especially when I start putting alphas and betas, like when I start doing, cosine of alpha minus a beta identity, and you're like, what the heck does that even mean?
Yeah.
Like I have to find a way to break that down into 2 different cosines. This actually breaks down into 2 different cosines and 2 different sines. So what's X and Y? I mean, that's an X over Y, but that's an X and Y over a different triangle because it's a different angle.
Okay.
So you're going to get lost. Right now, very basic identities. Yeah, maybe. We'll talk about why this is what it is later. The proof's in your thing, but we don't need it tonight. Are y'all seeing that? Let me show you one last one. What about 1 minus, I've got to think about it for a second. 1 minus sine of theta. And a cosine of theta on top. Simplify. Now, again, don't make the mistake of going, wait, I got an identity that has a 1 and a sine in it. No, you don't. You have one that has a 1 and a sine squared in it. So that won't help you here. Or will it? What's the last rule other than don't just stare at this problem? Create a monomial denominator. You know what that means? What do I have right now?
Do you do
A binomial denominator?
1 plus?
What if I multiply by the conjugate of 1 minus sine theta? But if I do it on the bottom, I got to do it on the top to keep myself honest. So check this out. What if I did this? Top and the bottom, right? On the top, don't even bother multiplying it out. On the top, I just get this. I can distribute it, but don't right now. Just wait a second. On the bottom, what do I get? 1. What happens to the outer and the inner when you have a conjugate? They cancel, and then you get what? Minus sine squared. Okay, now I do have an identity that has a sine and a sine squared, a cosine squared, and 1. So I do have one that has a sine squared and 1. Look at it. Sine squared plus cosine squared equals 1. So what would 1 minus sine squared be? Cosine squared? So I replace the bottom with a cosine squared. Oh, wait. What happens? I could cancel out one of the cosines, couldn't I? And now I'm left with 1 plus sine theta over a cosine theta. And that's not super pretty. Probably, honestly, on this problem, we probably would have put a cosine squared on there, so everything would have canceled nicely. But at least at this point, I really can't do much else, but I could go one of two things. I could say, well, I could just take the bottom part and rewrite it in the numerator since that was the first suggestion. So I could go cosine on the bottom is a what? A secant on the top. All right, at least I got rid of my denominator there, which I can't bring this up because it just doesn't work. You can't bring binomials, and you can't rewrite that as 1 plus cosecant. It just doesn't work. It just doesn't. Okay? So at least I got it to there, or I could multiply it out. 1 times a 1. So I'm sorry, 1 times a secant, and then a sine times a secant. So I might be able to do something, and right here, what could I even do with that secant? What if I change that secant to a cosine? What does this become? Tangent? Well, that's not bad. And no, that's not an identity, even though a tangent and a secant's together because of what? We're not squared. Another thing you could do right here is just right here. 1 over cosine, sine over cosine. You can do that when you have a monomial. But again, I made this one up. Most likely what would have happened is they would have had a cosine squared there, and you would have just canceled all that out, and you would have stopped right there. That's probably what they would have done for you at this level.
Why isn't it negative cosine squared theta? Isn't 1 minus sine squared theta negative cosine squared?
So if I subtract the sine squared theta, 1 minus sine squared theta, just the cosine squared, right? If that's the identity equals 1, when I subtract it from both sides, there's my 1 minus sine squared. It's equal to cosine squared. Okay. Now, if you had a sine squared theta minus 1, that would be me doing this, right? That would be me subtracting the 1 over, but then I would also have to get rid of the cosine. That would be a negative cosine squared. Okay. But it would just depend, and that a lot of people miss that. So you've got to think back on these identities. You have that fundamental page. That's what we're doing tomorrow on our quiz. Start out with a 20 out of 20. That's really going to help you, okay? Because I'm promising you that the double angles aren't as bad, but the half angles, people tend to struggle more on those. But it's because they wait till the night before to try to memorize them. You make flashcards tonight and start learning these guys, you're going to have a much more happy experience with trig identities. I'm telling you. A lot of you are like, I don't believe him. I'm going to try what he does not suggest. Don't be that guy. Just trust me. All right, I got 5 more minutes. How about this? I got a couple more. How about this one?
Oh, yeah.
Secant theta cosine theta minus secant theta. Any thoughts? No, actually, that's not the problem. Here's the problem. This is the problem. Think. Yes. Okay, what would you do with that? Any thoughts?
You can
Put the secant down as cosine.
Okay.
Or you can
You just used a fundamental identity. So he said a secant is 1 over cosine. That puts the cosine on the bottom. So I'm going to move that to here. Okay.
and then you can change the fraction to secant squared theta.
Put this up and make it a
Secant squared theta.
secant squared. That's one way to go. Actually, it's actually not what I did, but I like it better. Move that up. And now I have 2 secants up here. So secant squared theta. And that is what? 1. Ooh, I have an identity that looks that way. What is that equal to?
Tangent.
If tangent squared plus 1 is secant squared, and I move the 1 over, I get that, so that is equal to what?
Tangent squared theta.
Tangent squared theta. You know what I actually did? I didn't do that, although this is better, I think. Here's what I did. This secant could come down. I was trying to illustrate the add fractions. What do you do to add fractions? Common denominator. What do I have to do here to do a common denominator? Make that a squared. How do I do that? Multiply by a cosine theta over cosine theta. Okay, if I did that, I would get cosine squared and cosine squared. Now, what do I get when I add these? 1 minus cosine squared theta over a cosine squared theta. Oh, wait, what's a 1 minus cosine squared theta? Sine squared theta, because if sine squared theta plus cosine squared theta is 1, when I subtract the cosine squared theta, I'm only left with the sine squared. So I'm left with the sine squared on the top. What's a sine squared over a cosine squared? Tan squared. Isn't that the same thing I got the other way? Except the other way was much better. I was just trying to illustrate the fraction thing. How about this? This shouldn't be that bad if you know your identities. What's 1 plus tangent squared?
1 plus tangent squared.
Secant squared. Just straight up identity, right? What's 1 plus cotangent squared?
Cosecant squared.
Cosecant squared. Okay, it's a good start. What can I do with that? Change it to sines and cosines? Now you could change this to sines and cosines, but why would you do it? You already have an identity that helps you, right? So the path would be a lot longer. But here, what's a secant squared in the numerator? A cosine squared in the denominator. What's a cosecant squared in the denominator? Sine squared. That's a reciprocal identity, right? I mean, I guess another way to do it is say secant is 1 over cosine, and since it's squared, and cosecant is 1 over sine, and since it's squared, and to divide by that, I would multiply by the reciprocal. So you could do that, right, and get to here, but I just go, if it's a fraction, that goes on the bottom, that goes on the top. If it's all a product or a divising or whatever, there's no addition in there. Now, what is that?
Tangent squared.
Have to be tangent squared, right? Because I could put each sine over each cosine and get a tangent, and since there's 2 of each, I get tangent, or tangent squared. You with me? All right, get some practice on these tonight, but guys, please start memorizing your trig identities. Be the fun guys, the happy guys on this test, and not the ones that are like, man, I feel like I'm in the alley, bound and gnashing teeth and clothed in canvas sackcloth or whatever. Just don't be that guy, okay? Be happy. Because if you do well on this, we're home free, man. Most people do pretty well on the graphing trig functions and probability. Most people do okay on the probability. That's all we got left. Right? And what time are we going to be here on Saturday morning?
8, 6 o'clock.
No, get here at 8. I'm feeling if you can be sitting down at a table in the lunchroom at 8:45 Saturday morning, that's fine with me. You don't have to get here any earlier than that. We're going to start right at 9. So if you roll in here real early, it's going to be harder. And by the way, what I'm going to do is in the lunchroom, there's all those tables. Our test is yellow. Originally, I asked you if you wanted to pick the color, but they sent me the test, so I didn't have to print them, even though I bought a whole bunch of like $30 worth of paper to print them for you. Anyway, whatever. We're yellow. Okay? So you're going to walk up and find a yellow test and just sit down, and they'll be spread out all over the lunchroom.
Is it a 2-hour test?
2-hour test, 9 to 11, we're done.
I don't care. I'm getting there at 5. Before the sunrise.
All right, Mr. Hurry. So,
Please have good news.
so it's a little different since there's like 40 teams in it. everyone gets a guaranteed 4 games. And they're not really doing like a bracket at the end. But so I have one Friday night and then one Saturday morning. But even with the 7 o'clock, I'd still miss it. So this is where this dilemma is, because on one hand, I do want to be here to be a part of the math team, but then
Well, think about it this way, and I know it's easy for me to say this, and if I'm in your shoes, I would much rather be in a basketball tournament. You love basketball, math you're good at, you might love it, but whatever. I totally get that part of things. We had a guy a couple of years ago who was by far, well, not by far, but he was always 1 or 2 on our team, which is kind of you. And he didn't go to a state tournament because he was going to something he wanted to do. Granted, his parents forced him to do it. It was, they're not forcing you, I'm guessing. But they went skiing. And he missed a state tournament, and Homer's team lost by a point. And it was in geometry, and he had to live that down, that feeling. Now, I realize that you have a basketball team too, and you're not being there could let them down as well. I do get that. And just know up front, because these tests are required, you're going to take a hit. It's going to be like a 0 out of 30 on a quiz, which is going to hurt your average, but it's not going to be something that's going to hurt you. Yeah, so that's not going to hurt you. So I've had people do this before. I had Anna Claire Stone went to a concert in Atlanta till like 11 o'clock, drove back here, took the state tournament, and was still here. That would require you a lot of effort on your parents' part. I don't even know if they plan on going. Are they going?
I think my dad was, because my sister is also playing.
So that would be an enormous effort on his part. As a parent, I wouldn't want to do that. So that is an option where you could kind of have your cake and eat it too and only miss one thing. But it's a risk. If we didn't have Mountain Brook in our division this year, which we do, I would like our chances based on y'all's results last year. But they're a wild card, and they have the best math team sponsor in the state. He's a genius, and he can coach those kids up better than anybody. And if he does, we've never had him in our division. And we would need all of our guns, on the wall. So I can't tell you, I'm going to fail you if you're not there or whatever. I'm obviously not doing that. I have a set thing I do. But I really hope that you'll choose to be there. And maybe talk to your parents or talk to your coach. And even if you missed the first 2 and got the last 2 in, it's not like it's y'all's state championship, right? It's just a tournament you're in. I get it. AAU ball, is that what it is?
It's called the Atlanta Jam. It's probably our biggest tournament of the season as well. So it's.
But this is our state championship, the only thing we have. If it was Hoover, I wouldn't care. If it was the stadium, I wouldn't care. This is what gets printed in the math journal.
Yeah.
The Alabama math journal. This is what people look to. So it's a big deal for us. One of our best 4 last year, Homer said you were always the same couple. And then after that, there's so talk to your dad. If it's just one tournament, are you like a coach? I'm sorry, if it's just one game, like if you could go Friday, that's a huge ask. It's a huge ask on my part. Or it's a huge ask on your part for your dad to do that. Because that means, and if it's not, I guess you wouldn't have to test early. If you're going to miss that morning one, you could come back, sleep kind of in until 8:30, be done at 11 and drive back. What's your third game? It could be when? Okay, so you'd still get some sleep. Your dad would still get some sleep. It's a big ask, but it's for them.
Yeah, for the team.
Yeah. So I don't know. We've had people do it. Like I said, I know the Stones did this 2 years ago for our state tournament. And ironically, Anna Claire, who's like, most score never matters, placed. Yes. And her score didn't count for our team, but she actually placed and got an award at this particular one. So talk to him and see.
You can do the Friday night thing.
That would be a win for everybody. I know that one game, but you still be three of the 4. So maybe ask that again. Huge ask, but it would really help this.
Okay.
And we might look back and go, ha ha,
Here we go.
we didn't even need it. But we might look back and go, oh, we lost by a point. And if Kim was here, we wouldn't have. And you have to sit on that.
Yeah.
And I'm telling you, Tucker, what's his last name? I forget Tucker the whole time. And they bragged him about it too. They're like, we lost because you weren't there. This team, they hazed him to the point where he got angry one time as a junior. And I'm like, I didn't miss. I'm not going to you missed. So I don't know. Talk to him.
All right.
I know I'd appreciate it.
Chandler is doing test corrections.
So,
Hey.
We didn't start today, like trig
Learn more about.
what did you ask him?
We're starting trig today.
Trig identities.
Can I go to the thing?
Crawford is in my Spanish project. He's like the funniest thing. You know how he's like committed?
And it's when it's unstraight, it goes up here. I can't put it in a ponytail where it's like I just ride anymore. It's insane. You should see how much hair that was on the floor.
We won, guys, 7-0.
5 inches.
Scored 2 goals.
Yesterday.
Oh, wait, you can't put your hair in a ponytail?
Well, for volleyball, I put a ponytail and then I braid it and I put it in a ponytail. But I can't. I can put my hair in a ponytail, but when I like braid it
How'd you miss?
and then like all the hair just pokes out, it doesn't stay. And I
But you
can't
probably
do
don't
it.
need to braid it now.
Yeah, but I always for tournaments, like that's my always go-to hairstyle, and I do it all my tournaments, all my games.
Maybe you can have a new go-to hairstyle.
I like it short. It's like
Pigtails.
This team just like.
And I'm not able to like braid my hair.
Thing on top.
Put their foot like they were like.
My wife used to do that when I met her. She just would always have ponytail on top. That was kind of her,
Like that. I missed it.
She's not pretty wrong. Her hair's shorter than
And Megan, this girl on my side, my right. She was this big. They're like, get her, Megan. And I was like,
No, I don't do buns like that.
I was so scared. And she was just like, she was just
Boot it.
There's
There's no little things. I don't like it.
You don't have to, like,
yeah, I don't know if you want to go that route right there. Kind of look like a geisha girl or something.
I like her outfit today, Megan.
Thank you.
Oh, I got new sweatpants.
Yeah, but that doesn't stay in.
You get that from Jody?
Not for me.
Yeah.
I'm not using 2 hair ties. It crinkles my hair.
Oh my gosh, I thought this man was following me.
I know, but I don't know if
It
my
was
hair
so scary. In the top of the driveway, he looked at me through the mirror and he was like,
I'm not washing my hair today.
and I was just like, I was like, lock the doors for me in.
Not
And then we got our food
Is
and
there water bottle down there?
I only sweat about it.
well, what are the things you made?
like, I don't know, he was just like, and then he stopped his car. He was in front of us. He stopped his car. And I literally thought he was going to start following us. But when I tell you, he was staring dead at me. Please don't kill me. It's the last thing I need.
Going, absolutely not.
Did y'all hear about the body they found?
Yeah.
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 You're good.
7 a.m.
It would change. It really
Yes, you will end up getting in the car. Just that's.
I thought you said you want to get in a car accident.
Wake up. I have to wake up early so I can like have a few minutes to get out of bed. And
Yeah, I woke up this morning at 6 in the morning.
what's that 11 consecutive alarm?
But that's also because I
1
woke
minute
up at
apart,
6:30.
roughly.
Six
6:30 is that?
You don't have a snooze?
Well, I mean, I guess so, but like, what's like on an Alexa device? And so it's just easier, because I'll just like hit the button, turn it off, and then I know I'll just go to sleep, so then it's really annoying, like, it makes me very angry and violent in the morning, but it gets me up like 9 hours, like, hey, what?
Morning Martina.
It's like, I just have no choice, because it just keeps going every minute.
When I'm telling you, I have alarms They're like 5-minute increments from 6 in
That, I bet
the
that would be
morning
really,
to like
that's a hard start to
6:45.
your day.
So then I just thrown out, because I also have like my sound machine on, so I
Get some
can't
noise
hear my
canceling
alarm.
headphones.
My mom wakes me up and she brings me breakfast to my bed.
Oh
And
my
I'm
God.
and I just been sleeping. And I wake up and I eat a bit of my food and then I just go
You ever
back
need
to
a
sleep.
choir ride to school?
And then I lock my door. I
We
sit
got
up,
you covered.
I go lock my door so she can't come in. At 7:20, I'm falling back asleep. And
Yeah,
then I
but don't you have
realize-
those locks where you can like put the little thing in there and pop the?
Yeah, but she was getting mad at me.
My dad was in the military, so everything he did was like over the top. And he would go get a pan and fill it with ice water and get it like good and cold. And if I wasn't up by a certain time, he would walk in there and just dump it on me.
Oh my God.
I was like, what in the world? How about that? Son, get up. Yes, father.
My mom
Nope.
tries to do
Dump
everything,
water.
it does not work.
That's so.
I have alarms that will not turn off until like, I have to aggressively shake my phone. I'm like this.
Yeah, that's
And
what
I still
happens. They
fall
do like.
asleep. I do math problems.
That's what I was gonna say. Or they like make you spin around.
Literally,
Yeah, it does not work. I just go back to sleep.
Yeah, my son would sleep, like the alarm would be just, like, we had one of those digital ones, you know, that goes, it's just really awful. And it would just sit there 2 feet from his head, blaring, totally out.
That's crazy.
AP's my strict TV. I had
He-
to watch accidentally.
That dude
That's
sleep through anything.
My dad always tells the story of like his brother had to get up early for like a band trip or something, and he was really, really terrified that he was